Line W1, Learning Test 3, we're going to take a look at connecting up DC drives in order to go and control DC motors. Now, the first learning task, we just kind of examined what the components were that were inside of a DC drive roughly. The second one, we took a look at how we convert AC into DC that we can use then inside of either a DC drive or we can use inside of an AC VFD. And the third one over here is now where we're actually going to go and make those connections onto the drive itself. Once again, talking about the motor at the very beginning, the motor is going to go and need to be specially designed for these. If I'm going to go and utilize a motor that runs off of rectified DC, it needs to be suitable for that because a rectified DC waveform is going to be this humpy sort of look to it. That is going to be a lot different than a uniform DC waveform, which is going to be just flatline DC. And then if I go and take this humpy looking DC, the rectified that I have over here, and I then start to chop it, so, what happens is we get an even different characteristic. We're going to get this rapidly rising type of waveform. Anytime that I've got DC that is designed to, or DC component that's designed to operate on straight level DC, so completely rectified, completely filtered, constant values of DC, I don't have to worry about any of my shred losses, skin effect, hysteresis, radiation, eddy current, and dielectric losses because there is no change in the value. All of those shred losses come off of any time that I have got alternation. Or not necessarily alternation, but rather change inside of my waveform. So inside of these over here, I am going to have to worry about shred losses. I'm going to have to go and have DC machines that are going to have a laminated core that are going to be able to go and withstand rapidly rising front edges like these ones over here, and that are going to be able to deal with the rapidly expanding and rapidly collapsing magnetic fields that cause small amount of magnetic shifting. Because of that, I will need to go and make sure that I'm just selecting the right type of motor. So don't just hook up any old motor to a DC drive. If you have a motor that was operating without a DC drive before, you cannot necessarily put it directly onto a DC drive. You need to go and make sure that they're compatible. Motor's compatibility is determined off of something that's going to be called our power code, and our power code is just basically going to go and take a look all the way from smooth type of waveforms all the way to choppy type of waveforms that I'm going to go and have. What I'm able to do is I'm able to go and use anything that's going to go and be smoother. So if I have got a single phase full wave rectified with only 2 SCRs and a diode, single phase full wave rectified and driven, I'm going to be able to go and use anything from a K at the minimum all the way up to a over here. But if I have got a D, if I've got 3 SCRs and 3 diodes, so I'm going to go and have a semi-converter. Anytime I've got a semi-converter, I can only use classes D, C, A, etc. as we go up and through this one. Just the classing of the motor itself that is determining what type of supply it can be utilized with. So a D-class motor can be used with anything that's going to be seen above that one because it's going to be smoother. It's going to be easier for that D-class motor. Also, these DC motors do have to be able to go and operate at an overload. If we do have an overload on a regular system, it's just usually caused because we have got too much load that's been applied. But in cases of acceleration or deceleration, we're actually going to go and run a lot more current than what we normally would. During that acceleration, if it's going to take a long time, or during that deceleration, if that's going to take a long time as well, because we're able to go and smoothly ramp down using these. As a result, we do have to be able to run at 150% of our FLA for a minimum of 1 minute off of these DC motors. Okay, let's talk about our connections. Our connections are going to be identified by letters. Once again, these letters are going to be letters that we learned back when we started looking at DC machines. You should be very familiar with any time that you see an F that we're talking about a shunt field. That's going to be around the outside, many turns, small wire. It's designed to go and provide a lot of flux. Anytime that I have got an A, I'm going to go and be looking at armature. And if I have got A's and S's inside some of these drives, and we talked about this at the very beginning, that on some drives, what I'll have is I'm going to go and have all those terminals. I'll just draw in a bunch of sets of screws over here. I'm going to have a bunch of different terminals that are going to be connected inside of here. And I'm going to go and label these ones here. A1, A2, S1, S2, and then we'll make this one down here F1, F2. I'm going to be connecting my shunt field directly onto those two terminals. It's really easy. If it's, depending upon what the voltage is, if I've got low voltage, 150 volts, if my windings are each rated for 150 volts, I'd place them in parallel. If my windings are each rated for 150 volts and I've got 300 volts, then I would go and seriesing them up. So the exact same as what we do off of normal motor operation. These ones over here are oftentimes going to go and have the series that is going to go and be jumpered together coming from the factory. And then the series is going to go, in most cases, it's going to travel through the board. I guess I'm best off to kind of describe this thing as being a three-way switch. It's a semiconductor three-way switch that's inside of there. But inside of that board, we are going to go and have components. We'll just say that these are board connections over here. And then this is going to be the board connection as well. So this would be my negative. This would be my positive that I'm going to go and have over here. Inside of the boards, there's usually going to be jumpers or a selector switch that allows me to select whether I have got a separated series or whether I have got an actual series. If I've got the armature and the shunt field that are series together, the way that this is, like that, then I'm going to go and connect them across this if I cannot access that junction inside of the motor itself. If I can't access it inside of the motor, then I'm going to have to go and place it through like that, and I've got this series field that goes through. If, however, I have the option to go and split that apart, what I'll do is I'll remove this jumper over here. This will only go out to the series winding, and then this will only go out to my armature over here like that. And then what I have to do is on that board itself, I'm going to go and throw a little switch that's inside of here. That switch is just going to go and select, it's going to break contact, and it's going to go and select where I'm going to go and power. This one here will be selected to its own negative. This one here is going to go up to another driver so that I've got independent armature control compared to my series control. Once again, it just depends upon the type of the motor and the controller. Not all controllers will have all of these features that are going to be here. All right, S1, S2, F1, F2, P1, P2 are something new that you probably have not dealt with yet. Those are going to be my thermal overloads that are going to be inside of a switch or inside of a component. It's thermal protection that is going to be laid out inside of motors. And we'll bury them inside of motors, transformers, anything that has got windings so that we don't cook off those windings. Now, there's two main ways for us to go and sense heat from a motor. One of them is going to be externally of the motor. The other one's going to be internally of the motor. What they have over here with these P1, P2 is they're giving us a place where we can take our overload normally closed, or 95, 96 contacts, where we can take 95, 96 and we can just place them into P1, P2. From the factory, these are going to go and be usually jumpered out once again because not every motor has these necessarily. We do have other ones that are going to go and have what's referred to as a thermistor that is going to be buried in the windings. You need to know what that thing is. Thermistor. What a thermistor is it is a device that has got an NTC, or negative temperature coefficient. It's an acronym that we use over here. In other words, as we heat this thing up, it is going to go and have more and more current that it's going to go and allow through. The resistance is going to be dropping. And so what we'll have is it's going to be this really tiny little thing. We'll bury that thing inside of the windings itself, and then it comes out. It'll be inside of the motor junction box, and it'll just be two conductors that are super skinny. It's not designed to carry the main motor current. What we're supposed to do with this is we're supposed to go and connect this to an actual set of overloads. Okay? So we'll have a size set of overloads based upon the motor size. And then we just connect this thing across to our positive, negative, or if it's the case of AC, we'll attach it to our AC. What this does is this thermistor that's inside here acts as resistance most of the time. But if the motor starts to go and get hot, let's stick a bunch of yellow here for lots of fire and hotness. But if the motor itself starts to go and get hot, the resistance of that is going to go and drop. And as the resistance goes and drops, it is therefore going to go and let more current travel through, and that current, as it travels through, will go and toggle. It'll toggle this actual overload that we have over here, which should go and operate my normally closed overload contacts, which could be either in line with a set of contactor or, in the case of a drive, connected into the P terminals, the thermal protection terminals. So the thermistor itself does not necessarily go directly onto the board. The thermistor goes to external overloads in a lot of cases. However, There are going to be some where you've got coordinated, where it's a manufacturer. Let's say Baldor makes a DC motor and they make a DC drive. They will have some where it's just a direct connection. They've already got that little overload placed inside of their board, and all you have to do is connect those thermistor connectors onto them. Size everything properly. If we're going to deal with any sort of braking that's going to be inside of there, the braking is going to go and be applied by my controls that are going to be inside there, dynamic or regenerative. Regenerative is going to be where we're going to go and send power back in. Dynamic is where we are going to go and operate our motor as a generator for a little bit. And we're just going to use our prime mover. For dynamic braking, the prime mover is always going to go and be inertia, momentum, right? Which is going to go and fall away really, really rapidly as this thing starts to go and, deliver out. If I were to take a look at this one here, I've got forward and reverse that are going to be off of these over here. These are going to be interlocked so that you would not be able to go and toggle both at the same time. And in most cases, these are going to also be solid state controls, at least for smaller motors. Large ones will use actual contactors for. But if I were to go and fire both of my forwards, you would see that we would be passing current through from 2 to 1 through my series field. Note how this thing is downstream of that series field. This is why we need to go and separate this thing out. This is one of those places where we'd see that little three-way switch on our board, making that junction for us if we didn't have it. If we go into reverse, one there, would not want to do that. That would have been a dead short. If I go into reverse, then we would see that we would go and pass our current through in the opposite direction, and then that is going to go and once again drive our motor, changing that direction. Anytime that I lose forward and reverse and I want to actually brake the motor, I'm going to disconnect these, and then I'm going to go and reconnect these. Now these, you'll note that anytime that forward fires, this is going to go and open, so we would not have a complete path through here. Anytime that reverse would fire, this one would go and open. So guaranteed, anytime that I have got this thing operating either forward or in reverse, I'm going to go and have one of these sets of contacts that are going to be open. Sometimes both these contacts are going to be in line as well. They could both be up over here. That would be just as good as having one down here at the bottom, but they just drew it like this. I'm fine with that. But all that we see is that as soon as we open up these, we remove the forward or the reverse, it's going to automatically close on this, and then I'm going to have inertia pushing this motor around. I'm still going to go and have inside of my supply, they don't show it in here, but inside of your supply, remember that there is still going to be that field, F1, F2, F1, F2. If I've got dynamic braking that is enabled on my drives, I'm going to have to go and keep this field energized for a little bit after I go and shut down power. So it's just going to have a time off of it, etc. So the field will stay energized, and then we've got this magnetic field, we've got direction of thrust, we'll be able to generate current using our left-hand rule, and from that we could see that the motor action that it is going to go and create will be in opposition to the inertia. So it's going to fight back against this and slow that down. When it comes to our actual regenerative is going to be much more complex. Thankfully, they're only giving us one-line diagrams, so we don't have as much to go through, but it is going to be taking us feeding in. That's converter number 1 here, where I'm going to go and have this SCR. This is where I'm going to convert. I'm going to change that to DC going out over here. Once again, we would have to have an external field, right? We're not going to be able to regenerate, act as a generator, unless we've got a field for this thing to rotate inside of. Inertia is still going to be our prime mover. Inertia, like that. That's still going to be our prime mover. And what we'll do is when we quit driving forward, when we shut off the control, the signal to this, that's going to be doing my conversion to DC driving the motor forward, we will then go and activate this, and we'll make sure that we're lining up our pulses coming in with our AC supply with these ones so that it feeds back out as AC. It's just a conversion from AC down to DC, and then we can convert back to AC to take this back out. Okay, reversing is just done through reversing direction off of our armature. We talked about this, that if they're placed in series like that, we see them both reversing at the same time. DC motors, by the way, are much more susceptible to having massive overcurrents caused by reversing, by plugging. So in a lot of cases, we will go and provide additional protection that's going to be anti-plugging. That's going to be, if it's an electronic drive, usually it's just going to be a timed thing that's going to go and say, I'm not going to allow this thing to go and operate until I've timed out and made sure that the forward has been off for a certain amount of time before the reverse goes back on. Drives are fairly smart as well. Well, it's not smart, but they're designed so that they can go and sense. Anytime that I am dynamic braking, I would still be pulling power from the field. We'll just draw on the field, the shunt field winding over here. I would still be taking energy in from there and passing it out and across to this. And so my microcontrollers that are inside of here, and they all have microcontrollers. That stuff is so cheap and easy to go and utilize. What they're going to do is they're just going to be monitoring the current, because ultimately kVA in is equal to kVA out. And if I am taking current in here and then I am dissipating it as rotational movement, as generation that is then getting dissipated as electricity, as heat, that means it's ultimately still all coming in from here and from the inertia. And so as long as I've got a CT inside of my controls on that field winding, which is super easy to do once again, then I'm going to be able to go and monitor and know exactly how long I'm braking for. Really, basically, once the extra current goes away, when I first start braking, I'm going to go and have a spike in my field current, and then my field current is going to go and drop back down to where it was before when it finishes braking. And so my controller can go and, safely assume that when it goes back to, I don't know, we'll call this thing 3 amps over here, that when it spikes up from 3 amps, it's in braking. It knows that because we've applied the stop signal. And then when it sees it drop all the way back down to 3 amps, that it's finished. And at that point, it would depower that shunt field that we would have. If it has sensed that this thing has stopped, it would then be able to go and say, okay, now that we know that we have a confirmed stop, we'll be able to start this thing up in a reverse sort of direction. Okay, let's talk about just protection off of variable speed motors, and then we're going to go and take a look through all the rest of these, troubleshooting and startup things that we have. Protection for a DC motor is going to be based upon, once again, the machine itself, overcurrent and current limiting protection. That's going to be your fuses or your circuit breakers that are going to be upstream of your actual device. Overload is going to be inside of your converter. Remember that these converters, semiconductors, electronics, are cheap like borscht, which means that we are able to go and monitor stuff super, super easily. So what we can do is we'll monitor inside of here, but the thing is, this controller, when it's shipped out from the factory, it knows nothing. Absolutely nothing. So your job as the electrician is to program this thing. I cannot overemphasize how important it is to program this thing. If you do not program it, it is going to stay at the defaults. And the defaults for overload, it might say that the default for this thing, if it's a 15 amp drive, is going to be 15 amps. When in reality, you're using a 15 amp capable drive to drive an 8 amp motor. We would want this thing to be set to that actual 8 amps. So you must program this thing properly. Programming it properly is going to go and tell us about overload protection as well as overvoltage protection. And it's really as simple as you taking the motor nameplate, the motor nameplate data, and you reading that nameplate data. You'll take a picture on your phone, you walk over to the drive over here, and then where it asks you for the voltage rating, you'll input the voltage rating. Where it asks you for the current, you'll put in the current rating. That's literally all you need to do. Sometimes it'll ask for design codes and things like that as well, because that helps to fine-tune the operation. But yeah, the voltage and the current just need to go in there so it can react and correspondingly apply overload protection properly. Field loss protection is going to go and monitor the shunt field so we don't go into runaway. Overtemperature protection can be provided either through thermistors or it can be provided through us using external overload contacts. And then the last point over here is if my motor is running slow, the fan that is attached to the motor, remember most motors are going to be TEFC, totally enclosed fan cool, that fan cannot push enough air out. And if it can't push the air out, the motor's not going to get cool, which means we're going to burn out. So if we consistently operate our motors below rated speed, you got to provide some sort of external cooling. Blowers, things like that. Okay, startup and adjustments. They go through a series of steps over here. You guys have hopefully at this point started up some stuff working in the field. If not, it's just, good to know what the procedure is. The procedure is the first thing you're going to do is you are going to go and check that everything, corresponds. Wiring of the drawings, you're going to make sure everything is tight. You're going to make sure that electrical components are, able to go and move. Don't shove them in if you got power applied, but make sure with the power off that all contactors, things like that, are able to move, particularly forward reversing kinds. And then check for any unwanted ground. You can do that with your meter, checking to ground. Don't use that megger, especially not on drive. You'll nuke the electronic boards. They're not designed for that type of, kilovolts or megavolts that we can put out of these things. Then check and make sure that the motor itself is free to rotate. Sometimes when equipment is shipped, it is going to be shipped with blocks. Blocks are just going to be something that prevents it from moving around during transportation, because that can be really dangerous. So you got to make sure that that equipment is ready to go. And then you're going to go and check your incoming power. Then you're going to power everything on. Okay? Check everything, make sure everything is good to go and programmed. And then once you've got everything powered up, programmed, you start this thing on, preferably with the load itself not being driven, just spinning the motor. Okay, spinning a motor by itself is totally cool. If you can, spin that motor with just the drive. So you're going to bring this thing up to speed, back down. After that, let your millwrights go and recouple that thing. Start this thing from a low speed. Never start on the highest speed, just in case there's vibration or anything else like that. But you're going to bring this thing up to speed, all the way up, all the way back down. Make sure it operates across the full range. Then go and set up, the load onto it. And once the load is set up onto it, then go and enter your monitoring. On a lot of drives, you're able to go and see what the amount of current is. You can run through your loads. You can go and say, hey, this thing is going to be operating around here. You can take readings of what your loads are. I mark them on the inside doors of my cabinets because it's really, really handy if I know under startup, under the first time that I operated it, that I've got a DC motor that was rated for, 90 volts, and that this thing was a 8.1 amps is what that thing was drawing. Fully loaded, I'm running the process, so I want to be there the first time that they run whatever the process is, if possible. But I'm going to go and measure. I'm going to go and mark that on the inside, because if I come back in a year from now and the owner's like, yeah, this is a piece of crap motor that you installed for me, and it just keeps on stalling out and stuff like that. I turn the thing on and I see that thing sucking, 12.5 amps. That's going to tell me that that thing is overloaded. That there's either they're overloading their system, or that their system itself has just got extra friction. Maybe they haven't been greasing their bearings, maintaining the actual belts and, the components that they're driving along with that. It's just really good to have that initial. It's super handy if you've ever done long-term, work. When you start something up, run it under load for the first time, just take an ammeter reading off of it. On drives, we don't need to use an ammeter. Drives will just go and tell you. If it's a high-quality drive with a display, it will tell you exactly how many amps that thing is running at. If I get a drive that fails, common causes are going to be that I've got a blown fuse. Blown fuse is usually going to be indicative of a overload. So I'm going to go, first of all, check, make sure the thing is not jammed up. Then I'll go and replace the fuse. I'll make sure that if it's a stalled out belt that's carrying product on it, that I get them to shovel that product off or something like that. Then I'm going to go and start that thing up and see if it operates. Don't just throw fuses in and restart, because you end up going through a lot of expensive fuses. Other times it's going to be caused by loose connections or by circuit grounds that are going to be inside of, in a lot of cases, the circuit grounds are going to be inside the motor where the windings themselves have blown through. They give you this whole list of a bunch of different things to do, probable causes, symptoms, etc. What happens where. I'm not going to go through all of these ones here because most of them are pretty straightforward. Do make sure that you go through there. A couple of things that I do want to highlight. The drive unstable, in other words, that the motor seems to be surging or anything like that. A couple of things. IR drop, compensation set too high. This is going to be a programmable thing inside there where basically it is going to be my volt drop is all that they mean. Where I have to go and figure out how long is it from my drive over to my motor itself. Roughly, you don't got to be down to the inch or anything like that. Just kind of figure this thing out as far as, feet or meters are going to be. And then your gauge of wire, and then they should have tables inside of your manufacturer's documentation that'll say you need to apply for this amount of voltage drop. So voltage drop compensation would be that it's just going to bump the voltage up a little bit where it comes out of the drive to go and deal with the DC drop. DC drops voltage a lot worse than AC. So if I've got unstable drives, oftentimes that compensation has been set too high, and as a result, small changes in loading results in huge changes in flux. The other one is if I've accidentally gone into differential compounding. If I hook up one and I didn't get my series and my shunt fields connected correctly, I'm going to be operating in differential compound, and at that point, differential compound is going to give me, weird sorts of operations off of these things. Other than that, most of the others are pretty straightforward. Components that just are failing to go and pass through. Do note that most of my large semiconductor components are the ones that are usually going to go and be problems. It's either problems on the external wiring or the main current carrying components. Like we talked about in electronics, and we hit a bunch of test questions on it and everything, we say that usually it's going to be the main current carrying component that's going to fail. If anything, seldom is it going to be the rest of the control circuit. Check those main components. Usually they're going to be buried right in the back. They usually are heat sunk to the cabinet itself. They might be hard to get at, but you can usually pull the control boards forward only if the drive is worth it. Okay, if it's a small, cheap, 2-3 horse drive, it's probably not worth your time to fool around with trying to fix the drive. Just replace it and move on. But if it's going to be a large one, you can either replace it or you can pay to get these things rebuilt, resoldered. I mean, you send me a bottle of whiskey, I would go and resolder half of these boards that are out there, because usually it's just a matter of pulling out the faulty unit and then resoldering that thing back in. Don't actually go ahead and do that. I've got enough work, but I'm just saying it's super easy. All right, cheers.